previous climate. Oh, thanks, Ravi. Most of our recent Climate Link videos or Climate Link Tech Talks have been recorded, and they're available at this bit.ly link. So if you happen to have missed one, or if you want to share this one in the future, we'll eventually get it posted. Please share that link around. We've also got a newsletter, which Ravi writes to on an occasional basis, but usually when he writes, it's genius and it's great. And this is a great forum to share job opportunities. So if you're working at a company that's looking to hire, or if you're in the market and looking for something, please share that in the chat. Ideally, before we get started into the chitter chatter of the heat pump conversation. And also, if you want to share your contact info or LinkedIn, that's always really good too. It's a great way to build some community here. Our upcoming talks, so for June, we're working on CDR, or carbon dioxide removal, and it's looking good for that to happen. July or August, we're still sort of juggling around what it might be. Could be solar power related, it could be some machine learning for the energy industry, or it could be happy hours. So we're still trying to figure out July, August, September. But if you're joined on the meetup, you will get our announcements and you'll know what's coming up next and around the corner. And perhaps one of the most important things, and Ravi alluded to this earlier, Climate Link would not be possible without the support from Atmos, Atmos Financial, which is a climate-fossil bank. It's ensuring that your deposits are not being invested and or reinvested in fossil fuel infrastructure, fossil fuels, or other unsustainable investments. And on top of that, the returns are actually pretty good. And I don't work for Atmos, but I am an Atmos member. Is that fair to say?
Yeah. And I haven't updated the slides since the Fed changed the rate. Our top rate is 0.8% at the moment. So I don't know exactly what the national average is, but that is what our top rate is. So
cool. And there are other benefits from joining too, especially if you decide to be philanthropic with your balance. There's other things that come with that too. So there's a lot of good that can happen. And then we're going to dive into the talk here in a moment. And we've Vincent and Taylor and I spoke a little earlier today. We've decided to try to keep our questions to the end of the conversation. But so during, if a question does come to your mind and you want to share it, go ahead and do that in the chat box. And Vincent and Taylor will kind of keep track of that and return to that at the end of the conversation. And at the end of the conversation, if you'd rather sort of orally share your question, just raise your hand and we'll give you an opportunity to do that. Cool. All right, so we have two speakers today, which is awesome. And what's even more awesome is the two of them have sort of come together and coordinated their presentation. So I'm really excited to see how this is going to go. I'm not sure how that orchestration will go, but we'll see. And I won't steal their thunder on giving what a heat pump is or why or how. But maybe I'll do just a really quick intro. So Taylor is the CEO of Stow Energy, which is pairing heat pumps with thermal storage for residential applications. I hope I'm right about that. He comes out of ERG, so many of you probably know ERG, the Energy and Resources Group at Berkeley, which is super awesome. And I think there's a Otherlab history here as well, right? For
There's connections. Yeah.
There's connections. Okay, fair enough. And then our second speaker is Vincent, and he's the CEO of Gradient Comfort. And here we have a slightly different sort of target audience for heat pumps, where I think they're trying to help decarbonize buildings that would be otherwise a lot harder to transition into heat pumps. And he's also from UC Berkeley, yeah? What was your MECI? You must have been a MECI, no?
Right. For a while, I was doing research in ERG, so I had my toe in the waters at ERG for a while too. But yeah, I was in the MECI department.
Wow. Hey, so now you guys have really set high expectations, because everyone I ever meet from ERG is like awesome. I'm going to go ahead and thank you both for joining us, and I'm going to stop share, and I'll pass the baton to either one of you. I think both of you are co-hosts.
Well, I will share.
Okay.
All right.
And then I think what I might also do is pin the both of you. And let's see if the Zoom magic actually works for us on that.
Are you seeing the split screen? Or are you seeing the full screen?
Split screen.
Yeah,
And that unfortunately.
we're seeing the speaker note side.
I apologize for that. See if I can swap. No, that's also not good, is it? You're still seeing that, aren't you? Okay, let's try again.
The magic of switching to Zoom meetings from in person.
Yeah, gee. Let me see here. Gonna try just sharing this desktop, and then that will create less of a conflict. There we go.
Hey, magic.
All right. Ready to go?
Let's do it.
Hello, everyone. Thank you for joining. I love talking about heat pumps and often enforcing people to listen to talk about heat pumps. So when Hitesh invited Taylor and I to speak to a group about heat pumps, we were both very excited. And so thank you all for being here, and thank you, Hitesh and Ravi, for organizing. As Hitesh said in our intro, Taylor and I know each other. We both spun out of our company, spun out of the same lab, and so we decided to do this like both present thing because we kind of have a lot of the same motivations and background around doing this, and the way that both of our solutions address the problem is kind of complementary in ways. And so we thought it would be fun to just have a conversation between us with you all, rather than like both of us give overlapping pitches that were separate. So briefly, our goal here is to get you excited about the heat pump movement, which maybe we're preaching to the choir here, but also talk about some of the real challenges and the impacts that it could have. So there's certainly a lot of work to do, right? Everyone doesn't have a heat pump today, but we would like everyone to have a heat pump as soon as possible. So we're going to talk through some of the challenges as well, what we're doing to address some of those challenges, and then some other calls to action that we think could help the broader movement. And so in the next slide, yeah, we'll start with who we are. So we both spun out of a private R&D lab here in San Francisco called Otherlab. Otherlab does a ton of research for mostly government agencies. Like they have a lot of RPE grants, but also some private partnerships, and eventually spins out companies when that research has gone from, government grant level to commercialization level. And that's some version of how both of our companies got here. And I also think that we were kind of looking at the same, climate lens via some of the data that Otherlab had done. And so we both are focused on electrifying some big loads in the home, but we're kind of looking at different types of homes and, different ways of solving that. So to quickly introduce Gradient, I think that of all the times I introduced the company, I think I have a worse track record of introducing it than this picture does. And so I think this kind of tells the big story, right? It is a heat pump. It gives you your window back if you have a window AC. It also requires no building modification, and you can install it yourself because it goes through the window. And so if you're shopping for a mini split, this is going to be way faster to install, way cheaper to install, doesn't require permitting. And of course, as we were chatting in the beginning, if you're a renter and you have a landlord, you don't really need landlord permission to do this because it doesn't require any modification to the building at all. But the real reason we're doing it, our company mission is to cool the world. We really want to focus on eliminating carbon emissions from buildings to mitigate global warming, and also expanding access to heat pumps and air conditioners because they're important for people's livelihoods and important to protect people against the worst effects of climate change. So this is our first product. We have a roadmap, and I'll tease later on what our second product is, and also how we plan to scale to cover different sectors and different parts of the electrification and decarbonization challenge. So that's it. I'll pass it off to Taylor to introduce himself, and then we'll start jumping into some more of the problem statement.
Sure. Yeah, so you already met me sort of, Erg and such. I likewise love heat pumps and love excuses to talk about them. So My background is HVAC engineering, so I've been doing this in some form for most of my career, energy and heating and cooling. But homes are my favorite. It's just so personal and intimate, and to have the right to really help people make their homes awesome is really fun for me. So we're actually focused on single family homes, and we've targeted, like Vince, we're inspired by the same mandate, just a different segment. And this segment is dominated by ducted heating and cooling systems. And so we wanted to make a system that could go in and retrofit a bunch of existing homes in America, 50 million homes. So it's a combination. The strategy we have is it's a heating, cooling, and hot water system. Just like Vince's product, it is a air to water heat pump. So it makes water that's hot and cold and then uses that water to transfer heat into the house. And you've got, some flexibility about how to do that. You can do it with air, radiant floor, et cetera. Our go-to-market though is the ducted. And yeah, the idea is that once you're using water, it's easy to bolt on energy storage. So you can just use a tank of water and all of a sudden you have a battery. And so that's the kind of core technology that we've developed is around how to use this low-cost storage potential, multifunctional operation, and really optimize that so to create value for the customer.
So stepping back to kind of like why we both created these two companies, why we're both here. I'll start with kind of the problem statement that got us into the challenge that we're trying to solve. Next slide. So this is the data that I think at least I saw, and probably some version of what Taylor saw, that led us to start these companies. If you look at all heating, cooling, and hot water loads, it's more than transportation. It's huge. It's on track to grow rapidly. And at least when we first started the company, there was no one having heat pump meetups, or if they were much smaller, and I wasn't aware of them. And so we didn't see a lot of conversation around technologies that were needed to solve this, or how we could really decarbonize. If you go to the next slide, I'll show you where this total comes from. It comes from a couple of different areas. It comes from fossil fuel use in buildings. That's made worse by the fact that methane leaks at a pretty high rate. We're just finding this out recently. Since 2018, there's been a handful of studies that have come out looking at methane leakage rate, and it has such a high global warming potential that it almost doubles the carbon footprint of combustion in buildings. Next, there's refrigerants. Similarly, no one was really talking about refrigerants when we started. Project Drawdown was probably first to really have a broad audience listen to them about why refrigerants were a challenge for climate. And then lastly, there's the electricity that these systems use. And if you look, if you were to have 100% zero carbon electricity today on the 2020 part of this graph, you wouldn't even remove half of the carbon emissions from buildings. So we saw electrification, we saw solar and wind coming, we saw electrification of transportation, but we were like, that's not enough for buildings. We need more for buildings if we're going to decarbonize. And what more we need is we need heat pumps instead of combustion in buildings to remove fossil fuel use. And we need better refrigerants. Obviously, heat pumps use refrigerants as air conditioners do. And so if we are to electrify all heating with heat pumps and use today's refrigerants, it would not be a good solution because this refrigerant bar would go up instead of down. And then lastly, the grid has to be able to support all of these new electric devices, and the grid has to decarbonize itself in parallel. And so that's why it's important for us to make these devices smart and be able to shift loads and talk to the grid and be as efficient as possible so that we can help the grid remove carbon associated with this electricity. So that's what we saw. We started the company. We said, we want heat pumps that use better refrigerants that are smart and talking to the grid. We don't see them being deployed fast enough, and we want to figure out a way to make it happen faster. And the interesting thing about heat pumps, so we talked about this a little bit before, but if you're in engineering school and someone says heat pump, it means anything that moves heat from low temperature, from low temperature to high temperature. That includes refrigerators and air conditioners. If you're in the HVAC industry, heat pump means we're probably mostly thinking of an air conditioner that has a heating mode. And this tech is really new. In the HVAC industry, heat pumps are just now becoming popular because of global warming decarbonization discussions. But really, like, we have been heating buildings by burning things for literally a million years. A million years ago, we discovered fire. We found a stick, we set it on fire, and that's how we made things hot. The ability to make something cold didn't happen until really around 100, 150 years ago, which means if you lived in San Francisco 100 years ago, 150 years ago, you would not have seen ice. Like, ice doesn't exist. There was an industry around shipping ice from colder regions to warmer regions. And then finally, we developed the tech around the same time we were developing things like solar panels and transistors that could actually make something cold. And that's really what a heat pump is. It does it by moving heat from an area that's cold into an area that's hot. And that process is against the direction of flow of nature. So you have to put in some work to do that movement. And that's really what a heat pump is. And I think it's important to say that because this next part, what Chair is going to talk through, which is that, like, we are at the very beginnings of deploying this new technology.
Yeah, so this slide blows my mind, how most of the world as we understand it happened in the last century. All of these devices have happened concurrently. It gives you pause. But yeah, so air conditioning, like Vince was saying, it really met a coordinate. It was novel. It was the first time we were able to make things cold with the machine. Heat pumps are different. So heat pumps are fighting the million-year incumbent of fire. and so they didn't introduce a new service. They actually changed the quality and the character of it, but they don't provide it for the first time. And so as a result, the reason that we've seen heat pump uptake over time has actually been, it's been episodic. It's been the 1970 energy crisis. It's been, a big investment in nuclear in the Southeast that drove electricity prices down. And then utilities really needed to see load. And so they said, please install heat pumps. And so now the Southeast has a lot of heat pumps and the rest of the country doesn't so much. Now today, this chart ends at 2005, but we're still sitting at about 38% penetration for electric heating. And so what we're waiting for sort of is a change of values, a change of incentives, a change of economics. It's different than just a fundamental performance boost that you get from air conditioning. And this is a big deal because air conditioning, it's reaching saturation in the United States now. I think 95% of new construction comes with air conditioning. Over 90% of homes existing have air conditioning, but the rest of the world isn't there yet. So there's 4 billion more of these things to put out in the world. And we need to be very thoughtful about what we do here, right? Because we can put these out as one directional heat pumps and they only cool, and then we're still burning things to heat. Or we can start to position these things. We can catch this wave and deploy heat pumps in their place. And that's actually something that the IEA, which is the International Energy Agency, they're tracking this globally and trying to at least give the data to show what we need to do. And you can see historically, the growth of heat pumps hasn't been jaw-dropping, 7.2% a year growth globally. And that roughly tracks that of furnaces and other appliances. Is not noticeably faster. But to get to the net zero energy targets that the IEA is now tracking out to 2050, we need to double that growth rate. And so this is what motivates Vince and I. This is why we're out here, trying to figure out what these challenges are that we need to address so that this can take place. And so that's what we're going to talk about. Challenges. These are the ones that we've, there's more, but these are the ones that we think are really compelling and ones that we are able to tackle with our companies and why we became entrepreneurs. So the first one is first cost. And, you can find some very rosy pieces out there that talk about electrification being cost neutral to other things or, in certain situations. Definitely for new construction, I think now over half of new buildings are actually being built with heat pumps. But for retrofits, I think going to a builders group like the National Association of Home Builders it brings some real honesty. And they're saying, look, it's twice as expensive to do an electrification retrofit. And I think this is based on my experience out there installing in single family homes. This is about right. at least in California where I've seen. And there's a lot of reasons why. It's a multi-trade project almost every time. HVAC contractors, there's 118,000 of them. They average 5 people per company. They are high margin businesses. They are loading their costs by 50%. And the reason they're doing that is it's hard to acquire customers, right? And they wear a ton of risk. They get a lot of callbacks. And then every job is bespoke. You get standard equipment, but how you connect those things is completely custom. And so you're doing lots of scouting visits to plan your buyout and to resource your projects. And then inevitably your procurement somehow passes through Home Depot, which is always a bad sign and is a tank for your efficiency and economics. And so that's when you just raise up a flag and give up, right? So we got to change a lot of these things in order to make electrification something that's accessible. And so our companies are doing really, really meaningful things here. So Gradient just said, look, contractors, it's a big challenge, right? So let's take a path for a lot of buildings where we do not even have to open that, and let's just go direct to consumers and let them install. For us, we're trying to make things simpler for contractors. So we've made a whole lot of effort toward that. And we're also working on, instead of having like multiple heat pumps, almost every home, if you electrify, you have a hot water heat pump and you have a heating and cooling heat pump and a refrigerator heat pump. So there's lots of heat pumps in your home. We're trying to bring those things together into one product so that installation is simpler and you get more value from your installation so that the margin can be more attractive for a customer or for a contractor. Yeah. And so, just to talk more specifically about what we're doing, like I said, it's more functions of one product. We're set up to serve single family homes, and that's really our target. So ducted systems is our number one market. And then a big thing that we focused on is, in addition to storage and making that work, is productizing the complexity. So today, most systems that you see that are water-based, they look like this picture on the left. And it takes you about an hour of head scratching to figure out what pipe goes where and why. And that shows a lot of field intuition, right? That a contractor had to really think about things and coordinate them. We are packaging the complexity of water-based systems in products so that a normal HVAC contractor can do an installation that is water-based. So what you see on the right is our latest iteration of our control panel. So it is both a computer with low voltage controls that open valves and manage the heat pump, but also valves, air purge, strainers, all the different specialties that you need, check valves and things that would make a HVAC technician's head explode. So the idea is, let's just do simple connections at the edges and then put all of the complex sensing and compute and valving in a box. And so when you actually go to deploy a stow system, it reads like a line set, right? Like you're just doing a split system with refrigerant, but in fact, you're using plastic tubing, PEX, and it's water inside. And so it's actually quite simple to connect.
And then similarly, we saw a lot of the same info that Taylor mentioned around like installers are expensive. Not all of them want to do heat pumps. None of them know what they are. And the same thing around mini splits too, which are important for more efficient cooling. And so we said, all right, well, let's see if we can design a system that didn't require any refrigerant work in the field. And if we remove the need for a technician to do refrigerant lines, then we could remove the need for everything else too, right? We could remove the need to have a hole drilled through the wall and remove the need to wire electricity and just use a 120 volt plug. And so we did that by basically, sorry, I'm trying to just distract you by the chat, but air hotinator is a great name. We did this by basically using a secondary loop so that no refrigerant runs into the house. The secondary loop is low pressure, it's water glycol. It can be connected by anyone, and we use a double valve quick disconnect that just snaps in. So like you open the box, read the instructions, you click the hoses together, and it works. And this basically let us put mini split hardware, including heat pump capability, into a package unit that you could install yourself. You go to the next slide. we'll show a video. So the outdoor box is obviously the heaviest part. And when you're in a multifamily building with multiple stories, you don't want to put you don't want to have to screw a hole in your wall on the outside. So basically this bracket sits on your windowsill without any screws. It has a track that the outdoor unit will only slide if it's engaged in the track. It won't slide if it's not. And then lastly, it has air springs like the trunk of your car that let it lower into place. So you can put this hanging outside of your window pretty quickly, and also pull it out pretty quickly without being super strong, without spending a lot of time. And this is an important part to getting kind of the space and volume that you need for high efficiency, for heat pumps, for things like that. And so it's kind of the way that we got all of the technician work out of a heat pump or mini split install. And specifically it was because we said, kind of like Taylor's looking at the approach of like, let's talk to installers and figure out what they need to make this go faster with less equipment, with more integration. We said, let's look at customers for whom the installer is not practical right now, which is window AC users. And let's give them a solution to get what they need without an installer.
Yep.
The next challenge, they're not always effective. You hear a lot of people say, hey, these things don't work in cold weather. Also, I'll raise my hand first. We only certify to the regular heat pump test standard. We don't have our cold climate certification next. That is on our product roadmap, and it will be our next product. And so we can't cover a full load in the northern US, but we can offset some load. And one big goal for us and for the industry is to get capacities that are efficient at colder temperatures. If you want to go full electrification, it's necessary. And the technology now is here. There are plenty of places that have that are in colder climates that have heat pumps. There is some work to make sure that it's going to be sized appropriately, but it's possible to do. And then obviously, as we shift to electrification, having backup heat that is either electric or fuel based can be there for a minority of the time if necessary. And this plot basically shows with outdoor temperature how your capacity and your performance go. As the outdoor gets colder, it gets thermodynamically more difficult to push that heat uphill, if you will, to push that heat from the colder region into the hotter region. And that's why the capacity drops.
And you'll see some companies actually fib this, like they'll show a flat line. They'll say, look, we don't lose any capacity. But they're defying physics, right? It's actually just a control scheme where they're speeding up their compressor and they're tanking their efficiency in order to maintain capacity as a flat line. And then all of a sudden there's this massive drop because they can't redline their compressor anymore. So, if you see marketing claims to the contrary, it's just a smart control strategy to market the product slightly differently.
Our old company name for a while was TRO. Some people remember us as TRO, which was an acronym for thermodynamics rules everything around us. And it does. You cannot escape the laws of thermodynamics. And that is, pumps are no exception. If it gets colder, you're going to have to push harder. And then I think this is a great example of some data that Taylor found that shows that if you look at Europe and you look at where you have the highest adoption of heat pumps, it's in colder countries. And so it just is another data point to show that now that the tech has been developed to hit the capacities that we need at low temperatures, it's starting to, the adoption for those technologies are leading in some areas that are really cold. Also in Maine, 1 in 5 Maine homes has a heat pump, and Maine is obviously one of the colder, top 3 coldest states that we have. And lastly, New York City. So I think that this is important to mention for a couple of reasons. New York City has building decarbonization targets, which we're huge fans of. They're very progressive. They say that like if our buildings need to hit certain carbon reduction targets by a certain date, or they'll have fines. And so they're really leading the way with electrification. Unfortunately, you also need technology to match, right? You don't want to set legislation that for which there's no strong tech solutions. And we've been telling folks in New York for a while, Gradient, we've been saying, hey, if you do this over the windowsill, you can save a lot of the building renovation costs and construction work to electrify your buildings. And we've been saying we can do this with cold climate. Our first product's going to do half of your heating loads, and our next product's going to do all of it. And they just January this year came out with what they're calling a cold climate heat pump challenge. If you go to this article, it is a press article that just is talking about what New York is doing, and they mentioned us in it because New York basically asked for exactly what we were building: a no contractor, no refrigerant line work, 120 volt AC, over the windowsill heat pump. And so the fact that one of the largest cities with some of the coldest temperatures is saying this is a great way for us to electrify is big. And when we release this product, it will be the only cold climate heat pump that doesn't require professional installation. There's a couple other tiny heat pumps that don't require pro install, but they're certainly not cold climate.
Awesome. Okay. Next challenge. This one I'd say is not registered yet, but it is real. And I'm excited to talk about it. And I'm really curious what this group thinks about this, because it's a big issue that I feel like as a community, we're not really facing up front, and it could bite us. So and it's something that Stow is taking seriously and kind of banking on, actually. So I'm excited to discuss. And the challenge is alignment with renewables. Heat pumps, they run when the sun and the wind are not at their best. So for cooling, we all know about cooling and the evening peaks. Like in California, this is very, very common. You see, cooling really hit its climax right as the sun is falling off, and you get this confluence of factors where load's going up, solar's going down, you get a massive ramp, and you backstop it with a bunch of natural gas and imports from adjacent states. We are going to see a similar phenomenon on the flip side of this. When we actually use heat pumps, as they are for cooling, when we use them for heating as well, guess what? It's going to happen in the morning. It's going to happen in the winter. And what will happen is actually the peak of heating will happen before the sun rises, or right about when it rises. And then it will start to fall as the sun comes up. And so you're going to get the inverse problem. So the load is going to fall precipitously while the sun is going up. So you're going to get generation and dropping load. So now you're going to have the inverse operational issue that you have in the evening. And there's not that many places. There's 7 states right now that have winter peak events regularly. But there's a prediction that when we hit 50% penetration of heat pumps, 38 states are going to have this. This is from the NREL Electrification Future Study. And if you go to 100% penetration, then it's going to be all over the place. It could be, this is because of that electric backup, the peak heating events could outsize the cooling events. So what you see is actually, there's a lot of impacts here, right? There's just the viability of a renewables-led grid. That's one. Another one is consumer protection, right? You see here, these are the prices in California. This is the tariff that I pay, 56 cents in the evening. And that's driven by this nasty evening ramp, which is caused in large part by falling sun and rising cooling. And we're going to see that same thing occur in the morning. And so customers will be exposed to this. They'll be dependent on defending themselves with a battery or something like it. And if you scale this up, this was really fun. I was doing a lot of envelope math here, but it's 200 gigawatts of additional heat pump load if we electrify the rest of homes in the United States, 200 more. Okay. And that assumes no electric backup heat. That's all heat pump, right? So it could be double that if everybody's backing up with strip heat on the coldest day. And today we only have 10 gigawatts of demand response and 25 gigawatts of mostly pumped hydro energy storage. So if we want to not have this be backstopped with fast ramping gas, we want this to be a renewables grid, even in the month of January, we have to grow our flexible load resource dramatically, not just a little bit. This is like order of magnitude. And so when we think about, and if we're serious about low carbon heat pump operations in the future, we need to also be serious about energy storage and load shift. So how are we going to support this grid and make these morning and evening peaking products level out and align with the nighttime wind and the daytime sun? And so Stow has, this is a key constraint that we've taken into account when we designed our system, is that shifting to water solves a lot of problems, solves problems for events as well. But getting to water lets us use water as a fantastic high energy capacity medium. And we can make batteries for a third of the cost of lithium ion. And we can store energy for 70% of the load of the home. And depending on the conditions, we can get exceptionally good round trip efficiency and store a lot of energy. And it's scalable and modular, so we can store more energy or less depending on the application. And so the vision here is address the problem that you're creating with the device. Sometimes when you actually do it with a battery or some other patch, you're going to have to do interconnection and all other complexities. This is actually meeting the problem where it starts. And we feel like there's a real elegance and efficiency to that. And actually, Otherlab is pursuing that on other fronts. They're pursuing storage, backstopping, other electric appliances where they see, the need for that. So yeah, that's a little bit of a story. So I'm curious if you guys have questions or comments on this theme, or if we've heard other people talk about it. I would love to hear it, because even when I talk to really thoughtful people, this is usually a topic that is, 9th or 10th on their list. And I see it as kind of flashing red lights. So, and I'm excited about what we can do together to do something better and smarter.
Refrigerants. I could spend the entire hour talking about refrigerants, but I'm going to try to hold myself back. So the history of refrigerants is fascinating. What is a refrigerant? To be clear, our system has a secondary loop that moves energy inside with water and glycol, which isn't a refrigerant. We still do have a refrigeration cycle, but it's fully outdoors and it's factory sealed. Let's talk about refrigerants. You need some sort of refrigerant if you're going to do vapor compression heat pump, which there's lots of other non-vapor compression technologies that people are researching. They are a long ways off and we don't have time to wait for them. We are stuck with vapor compression for the near term. The refrigerants have been the major issue with vapor compression. So in the 1920s, when we really first started using more of these devices, we used ammonia as a refrigerant. It works great, it's efficient. It is not good for humans to breathe. And so eventually around the 1950s, DuPont invented CFCs, chlorofluorocarbons, and they don't have an odor, aren't toxic, aren't flammable, and work great as a refrigerant. And so they patented them. They sold them like crazy. CFCs grew up with the boom in AC, and it was great until we learned that concentrations of CFCs in the upper atmosphere lead to the degradation of the ozone layer, which is a thing that we really want and need. Ozone layer failing would have been incredibly catastrophic. And so we banned CFCs. The interesting part about the ban on CFCs, which happened with the Montreal Protocol, is that the Montreal Protocol was in part funded and supported by DuPont, who made CFCs, because they had a patent on a new chemical that would replace it called HFCs. And so HFCs, it turns out, super bad for global warming. And so this means that two of the biggest planet scale environmental disasters that we've seen, hole in the ozone layer and global warming, both caused in significant part by refrigerants. The Montreal Protocol was a great piece of legislation, and I'm not at all saying that it shouldn't have happened, but when you phase out a pollutant, you have to make sure that your transition plan to the next thing is going to be sustainable and scalable, and HFCs weren't that. We've now also phased out HFCs. The Kigali Amendment to the Montreal Protocol puts us on a phase-out schedule for HFCs. It's not fast enough. Project Drawdown, calling out refrigerant management, is the #1 thing we can do to mitigate climate change, was in addition to what's happening with Kigali, the phase-out schedule. And so we need to move faster than that. And furthermore, we need to look at what we're replacing HFCs with to make sure that it is not worse than CFCs and HFCs. So the industry is right now in this position where they're looking at, are we going to move to, or what's the next refrigerant platform we're going to move to? There's two kind of main options that I would say are the main two contenders. One called HFOs, another manufactured chemical with patents that we don't really understand the effect of dumping tons of this chemical into the atmosphere. Maybe that's an understatement. We're starting to understand it, and people are already starting to ban some of its byproducts. And so I myself am very much against HFOs. We will repeat this cycle. And if we're using these in every heat pump and air conditioner that needs to get on the planet in the next couple of decades, it won't be good. Natural refrigerants are chemicals that aren't manufactured, that occur naturally. They include things like propane and butane and CO2. And they're incredibly efficient. They're cheap. They have very benign environmental impacts. And this is the other challenge. If we don't pick the right refrigerant platform, we will cause major issues with scaling up heat pumps and air conditioners. And we both have kind of a similar approach to opening the door to some of these better refrigerants, and that is keep the refrigerant outside. This is commonly called monoblock, and I think that's a common term in Europe. But basically, all the refrigeration cycle is outdoors. It's factory sealed. You use a secondary fluid to move it inside. And this has a couple benefits. One, less total charge. Two, factory sealed system, it's really easy to prevent leaks. If you have a refrigerant connection in the field, that connection is just less reliable than what happens in the factory, because you've got human factors, you've got environmental factors. And so it's less likely to leak if you do it this way. And then lastly, if the refrigerant's all outside, you can use natural refrigerants like propane way safer, right? The amount of charge in these is way less than is in, for example, your grill. And we all put our faces over our grill and wave a match in front of escaping propane all the time. And mostly still have our eyebrows. And so the International Energy Electrical Commission, who sets standards internationally for refrigerants, has updated their standards to allow for propane if the right safety mechanisms are in place, so that it would never reach explosive concentrations if you spring a refrigerant leak. And it's things like that that will move us to platforms or refrigerants that won't be harmful to the environment. Call to action. Is this you or me? Is me? Is you? All right, let's do it. Call to action. There's a lot of things that we can all do. Taylor and I are obviously working on two aspects of this problem, which we both agree are super important, but it's not the only aspect of this problem. There's a lot of other things that need to happen before we can have what we all want, which is comfortable buildings that don't have an environmental impact. So we thought we'd give a quick shout out to both acknowledge the other challenges in this space, like financing, human interaction, workforce training, regulation, et cetera. To say that, we're not alone trying to solve this problem, and that there's a lot of other ways you can help. So anyone who's looking to work in this space, these are some companies that we called out as interesting. The way that these systems interact with utilities is super important. You want utilities to understand what their loads are and be able to smartly monitor and manage them. Policy, Rewiring America also spun out of Otherlab and is doing a lot of work to help educate federal government on what they can do to encourage heat pumps, both like encourage manufacturing, incentives for helping manage the install cost, et cetera. And then obviously refrigerant legislation is something that's going to play into the federal policy landscape as well. Electrification service companies, fintech companies that can help finance the install costs of these systems. One of the issues we see is that the all-in cost of HVAC is hardware cost, energy cost, and maintenance cost. And unfortunately, if you look at consumer buying decisions, they're only buying on first upfront hardware cost. It's really hard for a consumer to understand what life cycle cost is going to be and how long it's going to take energy efficiency investment to pay itself back. And so a lot of these fintech companies are helping by packaging all three of these costs into one service and helping people make the financially best decision and environmentally best decision. And then workforce training as well. One of the barriers we ran into is that contractors didn't always know what heat pumps were. And we're taking one approach to that, but obviously the more we can educate contractors in the installer base, the faster we can deploy things. Any other shout outs, Taylor, in this space that you think is exciting?
Yeah, I think I'm always proud when there's a utility that is forward thinking. So you guys probably all know Green Mountain Power in Vermont, but I would just always give them a shout out, and I'd track what they're doing. both developing business models to get products out to customers and, using both third parties and their own balance sheet in a creative way. And then Exelon is a longtime partner for Otherlab. They're an investor in us. They've got a variety of ambition and conservatism, but within their DNA, they've done some really nice things. Like in ComEd's got a dynamic tariff that they're doing in Northern Illinois with 25,000 customers, and they're really trying to learn at the margins about what they can do across their platform, which is cool. Yeah, and then the service companies thing. I mean, these are all young startups. I'm hoping that that sector will keep growing, but just front end people to help study a utility profile and help customers make decisions about what to do. I think it's closely tied with the fintech and how you can package something into a cash flow. But it's a real art and science together to do that and help the front end. Right now, we have poor HVAC contractors out there talking to a customer and trying to create a electrification roadmap for them, and they don't know how to do that. So we need a real slick way to integrate all of the information that we have and help people make long-term decisions.
Yeah, and appreciate the shout outs in the chat to other companies doing cool stuff here. Obviously, Taylor and I love to nerd out about this. And so we like keeping our eye on whatever, whoever else is helping at different aspects of the problem, or whatever other companies could be synergistic with what we're doing.
Absolutely.
Yeah. Let's see, next slide. So quick, few shameless plugs. You should definitely check out our website and pre-order if you want one. We're shipping to paying customers for the first time this July, which is super exciting. I wish we had way more units to ship, but I don't know if y'all heard, but supply chain is a little bit difficult right now. So we're scaling this as fast as we can. And if anyone is interested, we would love to have you pre-order. And on the next slide, other way that we would love help is careers. We're hiring quite a few people in a couple of different areas. We're super stoked that there's way more people excited to work in climate and way more people aware of what heat pumps are and what impact they could have. And so if you or anyone is looking to work more in this field, please check out our job openings. We're always looking for motivated people to come join us.
Cool. So we are really at an exciting place in our company's trajectory. We are just started commercial execution this summer. And so right now, a real hands-on way to get involved with us, if you're interested, is to, if you're looking for a heat pump for a home, and you think you might be a fit and you want to be, a catalyst in this whole story, go on our website and we have a way for you to kind of self-qualify. And then we can work together to, see if it's a fit. So we'd be really honored to have you guys go on there and check it out. And, send us, email feedback, questions. We're excited and early on the commercialization path. So really welcome your engagement on all fronts. And also we put a ton of information in the FAQs. So if that can really spark some good engagement there. Then I wanted to just put a plug in for this because this is kind of exciting. So we talked about that big 13% annual growth that we need in heat pumps globally. Something good is actually afoot, and it's this new policy that just was introduced by Senator Klobuchar this week, or 5/4, so not this week but this month. And it's called the Heater Act. And if you haven't seen it on the social media sphere, what it is it's a manufacturer incentive that would incent American companies that make, or people that make heat pumps here in the United States, and also make air conditioners, to stop making air conditioners and put in the couple of extra components that turn an air conditioner into a heat pump. And so what that means is, the consumer doesn't really need to be burdened or think any differently about anything, but all of a sudden the consumer choices change. And we've actually, as a public, invested in the right place, the lowest cost place to make that transition. Because once you actually get out to the consumer product of a heat pump, you've absorbed the overhead of smaller quantities, marketing material to overcome the inertia of fire. And so you don't have to buy all that, right? You just buy the valve and whatever the filtration you have to deal with in the refrigeration system. So so super exciting. And I put this picture in here. This is our friend Sam Kalish, and he works for Rewiring America, and he is actually in DC right now taking photos with Cory Booker and Amy Klobuchar, dressed up like a heat pump. And this is how things get done in Washington, DC. So hopefully, this will go through. Do call your congressperson, and especially if you don't live in California, and let people know this is happening and matters. I think this is the way to catch the air conditioning curve, right? If we can make this happen, it's a big deal. And then we're going to export this tech, right? We're going to start sending this to other parts of the world. So that's it. Thank you.
Yeah, thanks everyone. Love talking about heat pumps. I think I'm gonna call, after I call Senator Klobuchar, I'm gonna call Sam and tell him he should have dressed up like a gradient.
We're actually setting that costume is going to be mass manufactured. So if you want one, send us a note.
Really?
We actually have the cut files. We'll cut you one. Send it your way.
That's fantastic.
This was
go ahead.
I was just gonna say this was really good, Vincent and Taylor. Do you want to open the floor up to questions then? So there's quite a few in the chat, and if somebody wants to raise their hand, we could do a hand raise.
Yeah, let's see. Do you want to kick it off with grabbing one from the chat, Taylor?
Yeah, I need to get out of this sharing so that I can see people's faces. Hang on one second.
Yeah.
All right, I'm ready. Cool. Work from the front here.
Yeah, let's see. Shri had a question, and you also raised your hand. Do you want to just say it out loud?
Yeah, thanks. Hey, Vincent, Taylor, great talk and great products. So yeah, the questions are on kind of flexibility in the form factor, like horizontal windows, casement windows. So that's one class of questions. The other is like, can this be used for like PTAC units? Is that another flexibility that's available for the Vincent your product?
Yeah, great question. So we're definitely looking at horizontal sliding windows. We found that the vertical windows were the largest first market, but if we use these water glycol lines, which are super flexible. So adapting it to horizontal windows is really just a bracket change and industrial design change, especially when the heat wave hit the Pacific Northwest a couple of years ago. We saw a lot of interest for people who had horizontal windows are more common there. And they were like, we don't have a solution for this. We need something. So we're definitely keeping an eye on it. We hope to get there soon. It's definitely part of our mission, right? Like we built this flexible modular platform so we could get into as many buildings as possible. Was there another part of your question that I missed?
Yeah, so adapting this to the hospitality industry, PTAC units.
Yep, yeah, for sure. PTACs are, a lot of people hate PTACs. There's this building report that came out of New York called
So what is PTAC?
Yeah.
Oh, thank you. Package terminal AC. Most common way people see them is when you're in a hotel and it's the big box sticking out from under the window. So it's unclear yet. I think we have to talk to a lot of contractors and figure out for this specific customer what the best solution is. We would love to just seal the wall and then put in our current architecture, because you lose a lot of insulation if you're putting it through the wall like that. But if that's not the cheapest solution, maybe we have something that is effectively a wall seal with good insulation, but a small pass through for our tubes. So I think the answer is we're definitely on our roadmap is to get a better solution for PTACs, because people hate them and they need to be upgraded. But we don't really have a solution that's specific to that yet. I think the next question we have from Suri, I would love to hear Taylor's answer to this actually. So what's the efficiency of your water glycol heat pump compared to typical refrigerants? So I already clarified that we do use a refrigerant. We have like a water chiller with a secondary loop, which I think is similar to Taylor's. We use R32 today. You do get a small efficiency penalty in having that secondary loop. but the extra area we get by being below the windowsill and the addition of things like variable speed drives more than makes up for it. The biggest resistance to thermal transfer is air conduction. Water to refrigerant heat transfer is like many times more effective. And so that intermediary heat exchanger is definitely not your bottleneck. It's still getting heat into and out of the air. And so the ability for us to put in larger heat exchangers helps. And that's kind of the basic answer from our standpoint. But I think Taylor's system actually uses their secondary loop in a more interesting way. So I'll pass it off to you.
Yeah, it's conceptually very similar. Interesting thing about air to water heat pumps, and it's not actually so different from air to air heat pumps, but it's usually not seen or it's black box. But the efficiency and capacity of the product varies both on ambient temperature, as we discussed, but also on the water temperature that you supply. So you can, in a low condition, you can reduce the temperature of the water and dramatically increase the efficiency of the product. It's in heating or vice versa and cooling. And so what we've seen compared to, like, say, a Mitsubishi mini split system, there's a whole family of conditions where the air to water heat pump, wins. And then there's another set of conditions where the Mitsubishi wins. Overall, we are, our simulations in mild and cold climates are showing, strong benefit to the air to water system. Also, I think, as Vince said, like, we use a 4-row A-shaped coil in our air handler. So there's a lot of surface area. We're able to run our water loop very low at a very mild temperature, so that the compressor, doesn't have to push that hard, as we were saying, and it gets you, really, really good COP.
Let's see, Mark, you've got your hand up.
Thanks. Do either of you know, I mean, are there any cities, advanced cities, who are changing their building codes to force retrofits to electric and force getting rid of gas? I mean, they've shut off gas for new installations in places like Palo Alto, but are they, I mean, to get to net zero, we have to have heat pumps, right? So how is anybody forcing it yet?
I've only seen requirements to electrify in new construction, as you mentioned, in Palo Alto. I think Berkeley was the first city to do that. New York City just did it. And then the next thing I've seen is New York City's local law 97, which is going to fine buildings if they don't hit certain carbon reduction targets. And these carbon reduction targets are written such that you effectively have to get heat pumps. And so they've said, like, if reduce emissions by this percent or hit this fine, is a way of basically forcing heat pumps. There's no way to hit those targets without them. So that's as much as I've seen. Taylor, do you have anything to add to that?
No, yeah, I agree. I haven't seen anything more heavy-handed than that. I think honestly, we've learned 85% plus or minus 10% of installations of heating and cooling systems in the United States are emergency replacements. And it's like, call the guy, what do they have in stock? Let's put it in. And that's why, in that reality, we're out there going after the 10 or 15% of proactive people who are, like, either afraid that this is going to go out and they're going to be hot or cold in the next season. But to really do a wholesale change in existing buildings, that policy I just shared, the Heater Act, is like the master stroke. Because you're going to pick up that whole 85% of people that you're going to spend a lot of time trying to make them care. Right. Yeah.
There's
that works for cooling. What about the heating piece? Is there equivalent?
On both, there's a couple cities, since we're also getting a lot of ban the ban bans. So these laws on banning bans. So I've seen and talked to a couple of legislatures and things like that about essentially changing the code to require ventilation or another way to get around it. And basically, you can only so it's sort of the indoor air pollution. It's like, oh, if you're combusting indoors, you're going to have to require much greater ventilation. So if you've got an indoor combustion unit for your heating or cooking, then you make it too expensive, or just you change the economics by requiring much greater ventilation. But overall, yeah, as Vince and Taylor said, there's not a lot. And then I posted a PDF, sort of the genesis of the Heater Act, if you want to go deep into the details of how this is affected. And if anybody knows house flippers, so I was talking to somebody from the DOE the other day, and that fix and flippers is like a significant amount of home remodels is actually done by fix and flippers. And so we could get a pretty sizable amount of the retrofits would be by them if we can reach that group.
I think we're technically at the end of the Q&A session, a lot of time, Hitesh, but there's still a couple questions. Do you think we should pause
Let's keep
here
it going.
or keep going? All
If
right.
you and Taylor have time, I think we scheduled this till 6:30. So
Yeah. Taylor, do you want to grab a question next, or you want me to pick one?
You see, I am so not tracking. So if you're in an order, you can queue it up.
do you see Hitesh's question on the here, I can pop that into the chat again.
Oh, I think it kind of got answered. Taylor
Okay.
answered it.
Yeah, I'm fishing through here to try to.
Vince, how big of a space can the gradient unit do?
Yeah, so this launch product is 9,000 BTU per hour, which is recommended for 450 square feet in cooling. In heating, we find most of our customers are using it as a supplemental heater. It depends more on geography. So like you can't as easily correlate BTUs to size. And of course, BTUs drop more when you get below freezing. So at 46F outdoor temperature, we're 8,000 BTU per hour heater. And then as you drop down to about 20F, we're about a 4,000 BTU per hour heater. And we don't really recommend that for a specific size because this shouldn't be your only heating system. You should have a backup heating system. Short answer is 450 square feet in cooling.
I see John has an interesting question about carbon dioxide as a refrigerant. You probably have a deeper bench on that, Vince, but
let's see. We like carbon dioxide. I think that if you look at the total amount of carbon dioxide that we would need to use in these systems as a refrigerant, I haven't done the math, but I'm guessing it would be an incredibly tiny blip. In terms of sequestering carbon. And so as an example, do you remember it's like a kilogram a day is the average human's carbon footprint? Or it's a kilogram a year. Anyway, there's only a couple hundred grams of refrigerant in most of these systems. Still, it's a great refrigerant. It's a great refrigerant partially because of that same fact that I just said. If it all leaks into the atmosphere, it is very benign. In fact, R290, which is the refrigerant we're advocating for, has a global warming potential of 3. That bar I showed of refrigerant carbon footprint is because today's refrigerant has a carbon footprint of 2,088. If you were to switch to CO2 as a refrigerant, you would be 1/2000th the carbon footprint of refrigerants broadly today. It's also very efficient. The downside of it is 2 things. It's higher pressure. And so for us, we can't source a compressor that's sized for our system capacity. The most CO2 compressors for heat pumps are larger. Also, the thermodynamics work out that it ends up being less efficient on the hottest days in cooling. It's a transcritical vapor compression cycle usually, which just means that like the hot heat rejection side, if it gets too high, it ends up being a little bit less refrigerant. I think that ends up being in the noise, and there's a lot of advocates for CO2, especially in our team. Our system's really agnostic to what's driving it, and so if we get CO2 compressors that are at our size scale, we would definitely look into CO2 systems.
There are 2.
my experience too. Go ahead, Hitesh.
I was just going to say there are 2 hands up. Was Ted had a hand up and Raphael has his hand up.
Hi, Raphael. You want to go first?
Sure. Hi, Taylor. How are you doing? Good to see
Good.
you.
Good to see you.
Glad you've landed at an exciting position there. And Vincent, we haven't met, but we have. You may have seen an email from me across your desk a number of weeks back. A couple things. Taylor on Stow. I had prior conversations with Joanne around Stow, and I'm intrigued to see that Stow is now doing both air, space, and water, and water heating. One of the things that we're looking at in our strategy at Peninsula Clean Energy, which is load serving entity for San Mateo County in California, is how can we get all of the electrification in the smallest possible capacity, electrical capacity possible. And so I'm curious, with the addition of water heating, I want to confirm that we're still talking one heat pump, and how many 240 circuits are we talking about? And if you're still only, one 240 circuit, how are you dealing with possible contention between the hot water demand and cooling needs if they both happen at the same time?
Great question. Fantastic question. Yeah. So we are one heat pump. Yes. The default kit has a backup resistance heater in the water heating tank for just that reason. So if you do have a very design condition type cooling day, and you've got a big push for cooling, and the heat pump needs to be working on that for 3 hours solid, and yet at the same time you take a bunch of showers, you don't want to be in cold water, so you have a strip heater there to stand in. So the choices you have, you can get a nice healthy 240 volt 30 amp strip heater there, and it's a very low frequency use, so you could share that with an EV charger. You could use like a simple what do they call it, a simple switch, and
Right.
And share that circuit. Or you could lighten the spec and use a 120 and just have a little bit slower recovery. So there's some levers to do in that tank.
Okay, great. Vincent, on Gradient, we have an ongoing program now in low-income homes, where I think there is an opportunity potentially, literally like today, to start trying out your units. And would love to have a conversation about that. I think down the road, thinking about Stow, we're definitely going to be moving into whole home electrification on a broader scale. And so Stow is a solution there, I think is going to be very important. And when we get around to that, Taylor, I definitely want to touch base on that. But Vincent, if there's an opportunity for us to connect near term, that would be terrific.
Great. Yeah, my inbox is a mess, so I apologize because I probably missed your email, but we would love to chat. We're very excited about projects like that, and I think we're ready to partner. I'll also say that we've heard similar things from what you just said from New York folks specifically, that it's going to be the total electrical capacity connection into the building that will be the bottleneck to fully electrifying. They just don't have enough amps to fully have a cold climate heat pump in the entire building, which is why our device being Wi-Fi connected and things like what Taylor is doing to have storage on the device can help, because I'm not an electrical expert, but I believe the new electrical code allows for behind the panel management of loads, so that you don't have to anymore have your panel sized for every load at full blast. You can manage these smartly. I don't think that gets you all the way there in every building, obviously, right? Some will still need upgrades, but it's one thing that can help us scale electrification faster and cheaper.
Yep. So Vincent, I just put my email address in the chat, and I'm Director of Energy Programs for Peninsula Clean Energy. And so at your discretion, when you have a moment, just drop me an email and we'll schedule a quick chat. But really phenomenally important and great work that you guys are doing. So really appreciate it and look forward to working with both of your companies.
Likewise.
Cool. All right, was it Ted? Who's next?
Yeah, I think Ted had a question.
Yeah, I had a question I put in the chat too. Really curious about Taylor, about Stow's product.
Yeah.
Kind of like how it differentiates from current heat pumps. I think I learned a little bit additional of Raphael's question, but from what I saw is that it simplifies heat pump installation and management for technicians.
Yes.
Also offers power storage, opportunity for power storage, and then I guess also integrating hot water and space cooling and heating. Is there anything else that differentiates Stow's product?
Yeah, I feel like in a way, those are the ingredients. I think the result that might be more legible is that, we're positioning ourselves as the lowest carbon approach, right? Because we can shift and operate all three of those functions together. We can, especially if you're in a grid like California, where there's a lot of time differentiation to the carbon emissions on the grid, we're really competent in that type of environment. So if the environment really matters to you and you want to be supportive of the grid transition, that's I'd say that's a very core element to our story. Also, as there's time differentiated pricing, we are offering, this is energy storage derivative, but we're a protection for consumers, right? We're giving people the ability to adapt to a time differentiated tariff. And in so doing, you can have the lowest cost as well to operate. So in our experience, we're cheaper than getting a conventional, heat pump hot water heater and an air-to-air heat pump as well. So, and then the goal is, because we're doing all of those functions, we can also be competitive on first cost, including the storage. So the idea is, it's simple, it's integrated. The first cost is competitive with storage. And as a result, you're positioned for the future. You have the lowest carbon approach that you can buy, and you have, you have one system to maintain as well, and low operating costs.
And just follow up, thank you. I think you said at the very beginning that your first product is for, it's not for radiant, it's for forced air heating and cooling.
Yeah, so our system is fundamentally agnostic, as I think Vince has said about this approach. We make water, the water can do whatever it needs to do, but we've gone through a lot of effort, mostly because we want to actually deploy through HVAC technicians, and most of them know how to do forced air ductwork. And they actually also, a lot of them know how to do heat pump water heaters. So they're kind of a unique bunch of people that have a broad enough skill set that could install our whole system as one trade. And so and also more than half of homes, or 50 million homes ish, have ducted systems. So that's why we've really put a lot of effort into optimizing that as an indoor heat transfer means. But there's no reason why we can't do radiant floors. We have done a couple of pilots with radiant floors, and because they're difficult to characterize as a retrofit, it can be challenging for us. So we're mindful that there's gremlins in radiant floors, and often they don't properly insulate them when they're built, and so the system can disappoint the customer both before and after the installation. So you have to do a little bit of study before you would retrofit. I think for new construction, it's a slam dunk. I think it's a really cool application where we could do partly radiant floor, part mini split indoor, thing. There's lots of opportunities architecturally to, optimize how you transfer heat into a home moving forward.
Thank you.
Yep.
Maybe one more question, Hitesh. I think you've got a zinger to end us off with. Yeah.
I don't know if this is a zinger, but Taylor, you mentioned something that sparked the question. You mentioned something about trying to utilize the energy during lower emission times of the grid. And I'm kind of curious if either of your systems have integrated with a real-time forecasting data feed like watt times.
I'll go first. So we are using watt time in our logic. So when we optimize, because California actually makes watt times data stream available for free through the SGIP program, we are using that as a control input. So we can actually, one of our preset control algorithms is minimize my carbon, right? That's what I want you to do with this battery that you've just installed. And so that watt time is our source data for that. When we get we haven't established a broader partnership with them yet to do other markets, but because California has paid for it and set it up, we are using it. It's a really neat product.
And we have built our system with the hardware and the deferrability because we've got a Wi-Fi thermostat and variable speed drives. We can do a lot to modulate on shorter timescales and just finer degrees than a Nest can, for example. But we haven't done it yet. We don't have enough systems in the field. It's not important to our customers. So we want to get the platform out there that can participate in it. But if I'm being honest, like we haven't done it today, but we definitely want to.
Awesome. Way to plug prior Climate Link speakers too. We should do a collab. Bring Climate Link speakers back together that are now working together. Well, thank you both so much for this. Thanks everybody for coming. If you don't have heat pumps, get a heat pump, get their heat pumps. And yeah, if you're looking for work, they've got jobs. There's a ton more. Rewiring America. Climatebase.org is a great jobs board. I saw a couple people that are looking for work. First, go to their jobs boards, of course. But hopefully, we'll see you all do more in the space, and hope we'll see you back here again in June for our carbon dioxide removal talk. Should be about mid-June. All right. Thank you, Vincent Taylor, again. Thanks, Hitesh, for organizing, and have a great night, everyone.
Thanks all.
Thanks.